Hello guys, welcome back to MedZone African Motives. We are still on our revisions. Now we are going to have this as a revision. We had the introduction on our numbers, talking about the number system. So make sure that you watch the video on the introduction so that you'll be able to understand this exercise that you're going to be working on, which is our first exercise. But on this exercise, I shall introduce the last part, this one. We shall have it as an introduction because we never talked about this part, but the rest of the questions are just a revision. So I'm not going to waste much time. Remember, we talked about all the numbers that we are going to be having in our syllabus for the level of grade 10. So we're not going to repeat that part. Make sure that you just watch the introduction. All right. So we are given from the list of numbers, we have given -3, 3/4, the square root of 2, the square root of 9, 0 to -4. Write down all the first one. So we need to write down all the first part, natural numbers. All right. We are supposed to write all the natural numbers. That is our first question in this case. All right. What do we refer to as the natural numbers? That is the question. All right. Remember on our introduction, we talked about the natural numbers being the positive integers excluding 0. So we are going to be talking about the positive integers, but there we are going to exclude 0. So we are going to exclude, that is, we are not going to have a 0. All right. So we are not going to have a 0. So meaning to say we're talking about 1, 2, 3, and so on and so on. So on these numbers that we have, which ones that we are going to have under the natural numbers? So is -3 a natural number? The moment we have a negative, it is not. All right. 3/4 is a fraction, meaning to say we're talking about a decimal. So it's not. Again, you move on to the square root of 3 to the square root of 2. Can you simplify the square root of 2 and it gives you a whole number? If it can do that, then it means it is going to be bad. Let us check on our calculator so that we can move on together. The square root of 2 in this case, which is equal to, as you can see, this is not a whole number. This is not an integer. It's not a positive integer, it's a decimal. So meaning to say this is not, again. All right. You move on to the square root of 9. If we simplify the square root of 9, this one, we know that is going to give us a 3, but you can just confirm on your calculator. If you are not sure about your numbers, the square root of 9, it gives you a 3, of which a 3 that we are talking about, it's a positive integer part of this number. So meaning to say the square root of 9 can be part of our numbers. All right, we move on to 0. We said it's excluding 0 in that case. Excluding 0, meaning to say 0 is not part of these numbers totally. All right, you move on to 2. As we can see, 2 is an integer being positive. So we're going to take these 2 again. The square root of a negative, remember we said the square root of a negative is a non-real number. It cannot be simplified. You cannot obtain the square root of a negative. Remember your introduction, this cannot be simplified. So meaning to say this cannot be even be referred on our numbers. All right. So we saw that on the natural numbers, we are going to remain with the square root of 9. So we're going to have the square root of 9 and 2 in that case. All right. So we're going to have the square root of 9 and 2. We move on to the other part, which is now referring at the whole numbers. So remember, we said the whole numbers and the natural numbers, they are just familiar, only that the whole numbers, you include a 0. So meaning to say this time, we are going to just include a 0. On these natural numbers, we are just going to include a 0. So we've got the square root of 9 and 2 like that. So these are going to be what? Our whole numbers. So whole numbers, we are simply talking about what? Our positive integers. Positive integers, that is, we are now including a 0 on the whole numbers. All right. But the natural numbers, this one that you indicate with n, this one you indicate with n naught, to say that you are now including whole numbers. So these are counting numbers, all right? Number 3, the integers. So remember that the integers are positive or negative, or they can be positive, they can be negative whole numbers. So meaning to say we can include this time -3. We're going to have -3. All right, this one is a fraction. Remember, square root of 2, it gave us a decimal. The square root of a 9, we said it's an integer because it's a natural number, so it can be there. For the square root of 9, we also have 2 0, because 0 is an integer. Then also we have a 2. Remember, the square root of -4 cannot be simplified, all right? Then we move on to number 4, which is the rational numbers this time. All right, the rational numbers, remember, if you are referring to the rational numbers, you are referring to those numbers that we can write as a ratio of 2 integers, a over b. Remember, we talked about this, whereby a being an integer, b being also an integer, but b is not supposed to be equal to 0. All right, so let's start with the -3. Remember, I said all integers are rational numbers. So meaning to say -3 is a rational number. For a fraction, we've got a fraction 3 over 4. These are integers. It is going to be a rational number again. The square root of 2 is not, because we remember it gave us a non-terminating decimal. So this one is not. All right, the square root of 9, it gave us a 3. We proved that. So it's going to be part of our rational numbers because it's an integer. All integers are rational numbers. All right. You move on to 0. It's an integer, so it's a rational number. Remember, I talked about 0 on our exercise, on our introduction. I said 0 is same as 0 over 1. It can be 0 over 2. It can be 0 over 3. It gives us a 0. These are integers. All right. You cannot write 1 over 0. This one does not exist. All right. Then 2 also, that's an integer. So it's going to be a rational number. Again, the square root of 4 cannot be simplified. So it cannot be a rational number. All right. Let us move on to the other part, which is the irrational numbers. The irrational number is just opposite of what we had on the rational numbers. These are the ones that we are talking about non-terminating, non-recurring. So meaning to say we can't be talking of this because they were rational. So we can think of the square root of 2. Remember, the square root of 2, it gave us an endless decimal. So that's an irrational number. All right. That is the only number that we have. Square root of 9, remember, it gives us a 3. The square root of 4 cannot be talked about, that part. We cannot talk about the square root of -4. I mean, because that one, we said it represents what? A non-real number. All right. The number 6, they want us this time to list the real numbers. And I talked about the real numbers to say it's a combination of all the rational and all the irrational numbers. So meaning to say we are going to take all these rational and all the part of the irrational numbers. We are going to have it on our list. So we're going to have the list of -3, 3 over 4, the square root of 9. Yes, you can write them in an order, but here I'm just going to take the values that are we must have on our answer. All right, and also the irrational number, which is the square root of 2. So all these numbers must be on your answer because we said real numbers are a combination of what? Both rational and irrational. Like I said, please make sure that you go back and watch the introduction part. All right. Then we move on to the B. They are saying state whether each of the following numbers that we have here are rational, irrational, or neither of these two. All right. We also just a continuation this one. So let us check the first question. We've got the cube root of 33. All right. So the cube root of 33, can we find this? We can't determine the cube root of 33, but we can check that on our calculator so that we can be very sure if we can't determine this. So that is the cube root of 33. All right, we need the cube root, sorry, the cube here on this part, put a 3, then 33 like this, which gives us, so as you can see, it's an endless decimal, a non terminating, it does not end. So that means this one is an irrational number that we are talking about. All right, let us just say, remember that rational numbers are represented by Q, irrational numbers by Q bar like this. All right, so meaning to say this is an irrational number. All right, we move on to 2 pi over 2. Remember, pi, guys, is an irrational number. We talked about this pi on our introduction. So this is an irrational number. 4,103. So this decimal, this one that we see, it is ending. All right, it is a terminating decimal, and all terminating decimals are rational numbers. So that's a rational number. Then we've got 1 over the square root of 1 over 121. All right, we know that the square root of 1 is 1. The square root of 121 is 11. So it's going to be 1 over 11. But if you do not know this, guys, use your calculator to prove this. The square root of, put a fraction. All right, so you're going to have this as 1 over 121 like this. You are going to obtain 1 over 11. So 1 over 11, is it a rational number or not? Remember, a rational number, we said it must be expressed in the form of A over B, where we are talking about a ratio of fractions in that case. So if we consider this, we are saying it's a rational number because it can be given as a ratio of what? Of two fractions where A and B are integers. So this one is a rational number. All right, so that's where the square root of 1 over 21 is a rational number. Then we move on to 5, the square root of -2. The square root of -2 cannot be simplified. Remember, the square root of a negative, guys, we said it cannot be simplified. So it's not a rational, it's not an irrational number. This one, it's neither of these two. That means we are talking about a non-real value, a non-real number. All right, you can check on your calculator, but you must know that the square root of a negative does not exist mathematically. So that's the square root of a -2 like this. Oh, sorry, I forgot to put the square root here. The square root of a -2 like this. So that's math error to show that this does not exist mathematically. So we do not have this part in our mathematics. All right. Then here we've got minus the square root of 2. Remember, the square root of 2 can be simplified, but it's not a rational number. It's an irrational number. So if you multiply your answer by a negative, it means it does not change. It is going to be an irrational number. That's a non-terminating decimal or a non-recurring decimal. If you check on your calculator, again, like I said, guys, you have the calculator. So you're going to put minus, then this time the square root. This one is not square root of minus. The minus is out of the square root. All right. So you get a decimal. Yes, but this one, it's not recurring. All right. It's a non-terminating decimal. So it means it's an irrational value. All right. The square root of 2 over the square root of 2. If we are to simplify, remember I told you guys A over A gives us a 1. So if we've got the square root of a number and the same numbers here, these will cancel. You get a 1 over a 1. So that's 1 over 1 is a rational number because it's a fraction, a ratio of two numbers which are integers. This is an integer, this is an integer. So that means this is a rational number. So that's a rational number. The cube root of 27 plus 1. All right, if we add inside of the cube root, we are going to obtain 28. So it's the cube root of 28. Can we determine the cube root of 28? Yes, we can determine on our calculator, but it's not a perfect cube. So if it is not a perfect cube, it means that number is an irrational number. So that's an irrational number, this one, or we can check on our calculator, but we also talked about this. If you still remember, guys, we said we're going to have the cube root of 28 like this, which is 28, which is giving us an endless decimal that we have. That is a non-terminating, non-recurring. So that's an irrational an irrational number. All right, let us see. Then there is the same thing on C. They are saying on C here, state why we may conclude that each number below is rational. So automatically they are saying these numbers, they are rational, but you are supposed to give a reason. Why are we saying it's irrational? All right, 1 and 3/4 automatically by just looking into the number. Now they want you uh, to be mathematically cited to know by just looking into the number to say it is irrational or not. So remember, we said mixed numbers, they are rational numbers. So this one is because it's a mixed number, a mixed fraction. If you multiply this, you're going to get 7/4, which is a ratio of two integers. But there's no need for you to do that because you know your basics. If you know these basics, you just have to write your answer, which is the same thing as what we have also on number 2. We have a condition again of a mixed number, in this case, which is a mixed fraction. Then on number 4, on number 3, this 4, what can we say for this to be a rational number? What is it that we can say on this number? Is it an integer? We can write an integer because it's a positive. We can write it as a natural number, but the best that you can have there is a natural which covers everything, all right? To say it's a non-zero digit being a positive. Then a -5 now, we cannot write this as a natural number because natural numbers, they are positive excluding 0. So you can also have this here as an integer, all right, which is the same thing here. This one is an integer, positive or negative whole numbers. You can also consider this as a whole number. All right, so all these, they follow or they give us one and the same thing, which is what? Which is in this case to say this is what? This is a rational number, all right, to show that it's a rational number. Then, all right, why am I removing this? Okay, question 5, we're given 0.52. 0.52 is a rational number, which is very true because this is an terminating decimal. It is ending, this decimal, it ends at a certain point, all right? It is not a continuum where we are given and so on and so on. It means this one does not end, but this one, it has ended. We just have 2 digits after the comma, whether they are 4, whether they are 5, but as long it ends like this, it means it is a terminating. So we are having a terminating, and remember I said all terminating decimals are what? Are rational numbers. And the same thing with this part, again, it's a terminating. This one, we are having the same thing. We are having a terminating what? A terminating decimal. And I said all terminating decimals are what? Are rational numbers. All right, so you can even try to express them as fractions on your calculator. You will see that they give you a fraction of a over b, but here they just wanted you guys to know your numbers. Do you know them? By just looking into the numbers, can you interpret your numbers to say they are rational or not? All right, so be careful as you answer your questions. All right, on question number D, which is the one that I said here, we are going to have an introduction on this part. We never talked about this type of a question, but I told you guys that all recurring decimals are referred to as what? As rational numbers. We talked about that. But this time it's not about knowing that they are rational. We know that they are rational, but we want to prove, that is to show that they are rational, to show that recurring decimals are what? Are rational. Well, because we said they are rational. So all along we're just saying wherever we see a recurring decimal, we see a 0.1 like this with a dot on top. We say whenever you see that, you conclude that it's a rational number. You just write you do not even know what is happening. Why? You are just being told that it's a rational number. Now we want to prove that truly they are rational numbers. So how do you prove? I'm just gonna introduce and take 1 or 2 questions, then you do the rest on this exercise. So let us consider a condition that we have got a number, let us say 0,1. I'm just going to give you an example in that case. Let us consider that we have got a number which is 0,1 bar, which is the one that I talked about before. All right. On a consideration that this number here is terminating, because as we can see, it's a recurring decimal. As we can see that it is given a dot on top to show that it is given as 0,10, 0,1111, and so on and so on and so on. That is what it means. Remember our introduction of a recurring, guys. It means 0,111. It's not going to end. So what you're going to do is that you want to prove that it is what? It is a rational number. All right. So let us take this number that we want to show that it's a rational number. Let us introduce to be equal to x. So you're just going to say let x be equal to that recurring decimal, which is 0,11111, and so on, guys. There are so many. So what you're going to do is that you're going to just take one or two values so that we do not confuse, because here, as you can see, this is a repetition unless the number has got numbers that are changing. Here we are just talking about what? The numbers are the same. So you can even take even 4 digits after the comma, then you indicate this to say there are so many values that are thereafter. There are so many ones that we have. There are so many one that we have after that. So we just present that and so on and so on. So this, you let it to be your equation 1, which is x. All right. So the idea of this question is that you are going to multiply by the 10. You're going to multiply by 10. You multiply by 100. You multiply by 1,000 and so on. So the purpose of multiplying by these numbers is that we do not have a change of these values. These values will not change. Take a closer look, guys. If I multiply a number, let's say it's 5 times 10. What simply happens is that I just have to add a 0 there. If it is 5 times 100, I'm just going to have 2 zeros at the end, 500. So the number that you had before is still there. The only part that we have are the zeros. So this is the idea. We do not want to change our numbers, to change our question to say maybe it's 5. Now you multiply by 20. The moment you multiply 5 times 20 like this, it is now 5 times 0, which is 0, 5 times 2, which is, it has changed. We were having 5, now there's a 1. So we do not want that condition. So that's why we have to multiply by 10 and so on. So what is the purpose? All right, I'm going to tell you later on. I'm going to multiply by 10, by 100, by 1,000. So like I said, this, we are simply making sure that our values, they are not affected as they are. And we know that if we multiply by 10, if it is a decimal, like I'm given 0,12, to multiply by 10, I simply move 1 comma going to the right. All right, if I multiply by 10, I just move 1 comma going to the right. So this means it is going to be 1,2. So that's another advantage that we are going to have, or that we are going to notice. So if I multiply by 1,000, I'm just going to move 3 commas going to the right. That is going to be 1, 2, 3. All right. So if we want to have this to say, I multiply by 10, I multiply by 100, I know that, all right, if I multiply by 10 and I multiply by 10 again, 10 times 10, it's 100. If I multiply by 10, it's 1,000. So instead of me multiplying by 1,000, I have to simply multiply each and every number that I'm going to have by 10, by 10, by 10. You simply have the same thing. All right, so this is what I'm going to do. We are going to multiply this equation 1 by 10. All right, so if we multiply our equation 1 by 10, take note, 10 is going to multiply everything. So it's 10 times x, which is going to give us 10x. All right, 10 times this value, like I said, if you multiply by 10, the effect was that you are supposed to move 1 comma this side. Remember, our value is 0, 1, 1, 1, 1 like this, and so on and so on. So you're supposed to move 1 comma like this to your right, meaning to say your value was supposed to be 1 comma. We have got 1 comma here. These are the values that we're supposed to remain, which is 1, 2, 3. So there are 3 values now. Here there were 1, 2, 3, 4. All right. Now these ones are 1, 2, 3. So what are you going to do? Because you're supposed to have same number of digits after the comma. Remember this and so on means there are so many ones that are there. So of all those ones that are there, we are going to take one of it so that it matches the digits after the comma to say there are 4. The digits after the comma, they are also 4. All right. So that is what you're supposed to consider in that case. So this is going to be our equation 2. So in actual sense, you're supposed to multiply again by 10. All right. But now we are not going to do that, because what I want you to notice is that, all right, let me show you what you're supposed to multiply and so on, guys. You multiply again by 10. This gives you 100x is equal to multiply by 10. Here you move 1 comma. It is going to be 11 comma 1, 1, 1 like this. You are left with 3 digits. You put another 1 so that there are 4 digits after the comma, depending with the number of digits that you choose here are the ones that you're supposed to maintain to say, how many digits do I have after the comma? All right, you're supposed to maintain the number of digits after the comma, but that is not the major purpose. The major purpose is that once you do this, guys, you meet a condition where the numbers after the comma, the decimals after the comma are the same. You meet a condition where the decimals after the comma are the same. Not to say the number like what I was explaining to say, here we're maintaining to say there are 4 digits after the comma. No. To say here there's a 1, here there's a 1, here there's a 1, the numbers are the same after the comma. So if we check here and if we check here, the numbers after the comma are the same. We have 1, 1, 1, 1, 1, which is the same thing also here, 1, 1, 1. So on that condition, we can take any of these equations. So that's why I said here there was no need for us to multiply by 100, because already I have seen that these numbers here and these numbers after the comma are the same. We've got same values. So you look for the 2 equations where the decimals after the comma are the same, and then subtract your equations. They must be the same. Not to say that I have got 4 digits after the comma. The numbers are the same. All right, we shall do a question which does not have this 1, 1, 1, 1, so that you do not have a confusion. So like I said, you look for those 2 equations, then you subtract. So you are going to subtract in that case. So you can subtract equation 1 minus equation 2, it's up to you, or equation 2 minus equation 1. So to avoid working with fractions, with negative, I'm going to subtract equation 2 minus equation 1, because 10 minus 1, it gives us a positive number there. So I'm going to use equation 2, just equation 2 in short. So that's equation 2. I'm going to subtract equation 1. All right, so by your equation 2, you subtract this side of x together. All right, so you're going to subtract that side of x together. That's 10x minus x. All right, so you're going to have 10x minus x, which is equal to, you subtract this side, equation 2 minus equation 1, what you have on the right hand side on the numbers. So it is going to be 1 comma 1 1 1 1 like this, and so on and so on. So here there's no need to show because those ones are the same. So I'm just going to leave it like that. Minus, I subtract this one from first equation, which is 0, 1, 1, 1, 1. Like I said, I've got 4 digits, 4 digits. All right. So since this, so remember the purpose now of subtracting, it's because we said the digits, that is the number after the comma, are the same. So if they are the same, when you subtract these digits, these values, or these numbers after the comma, they will cancel each other. 1 minus 1 is a 0. So we are going to obtain nothing there. We are going to obtain a 0 because these numbers are the same. That's the purpose of us subtracting. I hope we are together now. So we are going to subtract this side 10 minus 1x, which is 9x is equal to, you subtract 1 minus a 0 in this case, which is 1. Remember, this part and this part is cancelled. There's nothing that is remaining because they are the same with these values. So they will cancel each other. So we're just left with the whole numbers, which is 1 and a 0. So that's 1 minus 0, which gives us what? Which gives us a 1. So that is the idea of your question. Then from there, to find x, remember we said let x represent what? That recurring decimal. So meaning to say x is going to represent the same recurring decimal, but as a fraction now. So you're going to divide by 9 to solve for x. So that's x is going to be 1 over 9. So as we can see, x being 1 over 9, which is the same recurring decimal that we had 0, 1 and so on. All right, let us check on our calculator. Is it the same as what we are talking about here? Because we will say, you might think that is something that we actually does not exist. All right, this is what we have on our calculator here. We remember we obtained our answer as 1 over 9. 1 over 9 as a decimal is what? 0, 1 like this. This is to show that it's a recurring decimal. If you press this again, it gives you 0, 111 ends up to it. It does not end. It does not end. So as we can see, it's truly 1 over 9, which is the one that we are having here. And this 1 over 9 is a rational number. Why are we saying it's a rational number? It's a ratio of what? A ratio of two fractions. I mean, a ratio of two numbers, which are integers. A ratio of two integers. 1 is an integer, 9 is an integer. And we said this number is not equal to 0. So that is how we are supposed to answer these typical questions. So like I said, on this question, it does not actually make sense because we have 1, 1, 1, and you think that when you subtract that part, you just need like two equations. No, you don't need two equations. You must have a part where the numbers after the comma are the same. All right, let me put it this way so that you can understand me properly. This one, you can be able to understand me properly. Let's say we are given 1, 575. All right, 1,75 like this with a bar like this. This one is a recurring decimal. We want to show that this is a what? A rational number. We want to show that it's a rational number. So to show that it's a rational number, it must be expressed in the form of A over B, where A and B are integers. So how can we do that? All right, like I said, the first thing you're going to introduce x. Let x be that recurring decimal, which is 1,75, which is this part is repeating 7 and 5. The part that is got the dot is the one that is repeating. So there's 7 and what? And 5. So you're going to have another 7, 5, another 7, 5, and so on, guys. This is what you're going to have. All right. So I'm just going to use 2, 4, 6. These 6 values, they are enough for me. All right. So I'm just going to use these ones. Okay. This is your x representing what? Your equation 1. So like I said, you're going to multiply by 10, by 10, by 10 throughout. So if we multiply this equation 1 by 10, let's say we've multiplied our equation 1 by 10. What is going to happen is that we are going to multiply 10 times x, which is going to give you 10x. All right, we multiply this by 10. Remember what I said, to multiply by 10 simply means you move 1 comma to the right. So it was 1 comma. So if I move the comma, it is going to be here. So it's going to be 17 at this point. That is where the comma is. And these numbers after the comma, now we are left with comma, 5, 7, and 5, 7, and 5. These are the numbers that we are left with. But if we count, there are 1, 2, 3, 4, 5. Here there are 1, 2, 3, 4, 5, 6. You are supposed to maintain same number of digits after the comma, like to say how many numbers after the, you are supposed to maintain that. All right. So if we follow the order of 5, 7, 5, 7, 5, 7, and so on, if this number is 5, it means The next digit was supposed to be what? A 7. The next digit, a 5, a 7, and so on. But us, we just want a digit that is going to normalize to have what? 6 digits after the comma. So we're going to just put a 7 there. So that was going to give us 17,575757. So we compare now. We have to compare, guys. All right, because this is our equation 2 now. It's not about you just multiplying, keeping on multiplying and multiplying and multiplying. No, you are supposed to compare at this point. Am I having a condition where the digits, the numbers after the comma on this equation 2 are the same, like in terms of this, I'm having same values? All right, here there is a 7, here there is a 5. They are not the same. Here there's a 5, here they are not the same. If this is a 5 here, this must also be a 5. If this is 7, this must be a 7. If this is a 5, this, so meaning to say these ones are not the same. So what am I going to do? I'm going to multiply again by 10, all right? So again, let's multiply by 10 and see what's going to happen this time. So if we multiply by 10, that is going to be 10 multiplies 10x. So 10 times 10, that is 100x, which is equal to, you multiply this equation by 10. Remember what I said by 10? You simply move 1 comma to the right. So if I move 1 comma to the right, it means the number is now at this point, which is 175. So we are supposed to have our number as 175 comma, because the comma it's now here. You moved it, it's now here. So you remain with 175 here. But if the comma is at this point that we are indicating here, what it means, you are going to be left with the number after the comma, which is 7, followed by 5, followed by 7, followed by 5, followed by 7, which is 1, 2, 3, 4, 5 digits after the comma. But we are supposed to have 6 digits after the comma, just like what we did from the first equation. So which number follows? 7, 5, 7, 5. So meaning to say 5 is going to follow after 7. So this is our equation 3 now. All right. So before you multiply again by 10, check if you have a condition where the digits or the numbers after the comma are perfectly the same. They are the same in terms of their presentation, like same values at each point. So let's check. Remember, we said equation 2 and equation 1, they are not the same, because here we start with a 5. Here we are starting with a 7. So they are not the same. All right. So equation 2 is what? Let's compare equation 2, 3 and 2. Again, 3 and 2. Here we've got a 7. Here we've got a 5. So these two cannot work. So equation 2, let's put it out. Let's go back to equation 3 and 1. Equation 3 and 1, after the comma, you're checking these values after the comma. 75, 75, 75. This is what we have here, 75, 75, 75. Exactly what we have on equation 1, right? Exactly what you have on equation. Once you see that this is happening, you subtract your equations, all right? These are the steps that you just take, guys, all right? These are the steps that you just take. So you are going to subtract your equations. So to subtract, remember, is to get rid of these numbers, to remove them from our equations. So we are going to subtract. So to subtract, like I said, it's going to be this time, since we saw that is the same from equation 1, 3, and equation 1. So we're going to subtract. So it's going to be equation 3 minus equation 1. All right. Equation 3, which is this side, it's 100x, and equation 1, it's x. So it's going to be 100x minus x is equal to, we subtract on this side again, equation 3 minus equation 1 on the numbers this side. So equation 3, that is 175,75,75,75 minus, you subtract from equation 1, that's 1,75,75,75. So that is the idea of your question, and the advantage of maintaining the number of digits after the comma being equal, like 1, 2, 3, 4, 6, up to 6. It gives you that assurance that here when you subtract, you are simply going to cancel everything because they are the same, and we also have same number of digits after the comma. So those ones, they do cancel. So here let's subtract 100x minus x. It means 100 minus 1, which is 99x, is equal to, since this part is cancelled with this part, you are going to remain with 175 minus 1 in that case. All right. So if we subtract this 175 minus this one, you are going to remain with 174. So that's 174. So we can divide, guys, to obtain x. Just divide by 99 since you are multiplying here. So therefore, we are going to see that our x is going to be given as 174 over 99 like this, which is a rational number because we have expressed it as a fraction, as a ratio of two integers. Also, this one you can reduce. You can check if it reduces further on your calculator. Maybe it reduces further. We can write the simplest answer. That's 174 over 99 like this. So it can be reduced further. That's 58 over 33. So this one is going to give us 58 over 33. Guys, it's the same thing like this one, all right? 58 over 33 is just one and the same thing. Just that you might want, or you might need to express your answers in simplest form. That one, it's up to you. This is up to you, guys. You can write it in the way that you understand. So like I said, these are the typical questions that you are going to be given and that you're going to work with. And this is an introduction on the part that you are given to actually understand like how to work those or typical questions that you are given. So this is the same situation that we are having here on this exercise, where we are given to show that the following recurring decimals are rational. So we are given 0.4, everything. So it's just a repetition of what we've been talking about. All right. So I want you to try these questions and see if you properly understand how your questions are given. So that will be the first exercise that you're going to try, but we are going back to revise this exercise together. So I want you to try this exercise as an individual, so that when we revise this on a separate class, you understand where exactly you made a mistake. So like I said, we are going to work on these questions on a separate class.